mission guys because he's planning to start his mission test
On the 12th. That's right. Well, that's what I'm saying. We're going to meet the 12th date.
The computer industry is one of the world's most important businesses. IBM is the leader of that industry, and STD is really the heart and lifeblood of IBM. In spite of the problems that come with size, STD is more exciting than ever, and across STD laboratories, our developments are of great importance to almost every business, industry, school, or activity of man. In the months ahead, we will see very significant strides in the application of computer systems and new and exciting ventures. There is a tremendous span of activities underway across the laboratories, and I wish I could better convey the sense of pride and excitement that I feel as I travel through the laboratories and see the new technologies, new systems applications, and the creative work of the people in STD.
Where does a story of excitement begin? Maybe on a chalkboard.
We see a good example here of how IBM locations in various parts of the world are working together to bring a project forward. The initial...
In Raleigh, North Carolina, this is Hans Huth talking about work on a new kind of terminal. It's an interesting one. It gives out money.
Then worked with ASTD and Lloyds Bank, a leading-edge customer in UK, to define the product requirements. A key role was played by STD Hursley, who defined the line control for this terminal to match the existing 3980 system that Lloyds have installed.
The cash issuing terminal lets a bank customer get cash at any of its branches with a magnetic card. She keys in a security code and the amount of money she wants. The bank's computer verifies her account and does all the figuring. If she's got enough in her account, the amount she asked for is subtracted, and she gets the money. It takes about 30 seconds. A security feature lets the terminal swallow any cards identified by the central computer as lost or stolen. Right now, this terminal is getting its finishing touches. The Lloyds Bank of England, at the British lab in Hursley, one of the many that work together to put it together. The cash issuing terminal is one of many new terminals STD is working on to bring more computer value to more users. Terminals are helping our people right now. In this system, for example, developed in Poughkeepsie and Boulder. It's called ClearCaster. What it does is help programmers develop their systems right at their own terminals. They can test, correct, and change their programs without leaving their work area. Saves a lot of time and effort for Yadish Nada in Boulder.
I found using Caster is much easier. I can work in my room, and I can save a lot of time by not using cards. I've just updated my program, and now I'm going to use a tool called Debug to test it out before I schedule it into the machine.
In Poughkeepsie, ClearCaster has helped develop a new advanced operating system. Among the many programmers involved in that effort is a group called the Project Office. It coordinates and controls that effort, designing, testing, measuring, analyzing. They really work at it.
On this, and what do we keep that or not?
Well, during the process. But you can't just take it from, I don't think you can just take it from one place. I think you have to take the whole schmear, you put new code on, you're going to have problems and bugs. But it's just not going to knock you flat.
No, but that's wrong, because all through June we do the mission test. That's where the guy is testing his code to see if his code works in the system. After that, you do the system test to see how those things interact. When something blows up, Then you got to go back, and it's usually more than a one-component hit by definition, because you haven't tested those things together yet.
Look, I'm all for testing this stuff, you know, together and early and so on. But what I'm concerned with is that in this early period.
What's happening here is a sort of final assembly of the operating system. And it's the key to top performance for one of our best-known products, System 370. It's already a classic example of the way our labs interact to come up with a major product line. The low-end additions to 370 are under development at the Böblingen lab in Germany. Here, an entire system is being operated and serviced from a terminal console. It's an innovation that adds both efficiency and convenience. Here's the 135, engineered at Hursley. It's the first 370 system to be developed in Europe. Endicott developed the 145, first of the 370s to use monolithic memory. And the top-of-the-line systems were Poughkeepsie developments. But the development process never stops. Engineers at several labs are setting the stage for a new direction in data processing. They're modifying System 370 for virtual storage, one of our most significant developments. This new concept, encompassing all of System 370, projects a larger main storage capacity than really exists. Virtual storage saves time and space by bringing active programs and data from input devices into main storage, only long enough for execution. For example, in some customer environments, there are some application programs that can't run because of core availability. Now with virtual storage, they can. This means main memory is organized better and used better to make System 370 more efficient, more flexible, more productive, from the standpoint of both machines and people. Putting new innovations to work is the name of the game in SDD. In Kingston, they're working on FET memories, packaged on tiny chips, like this. Developed by the Components Division, that little thing can hold more bytes of storage than a conventional core memory as big as the sandwich. Let's just try to get 1,000 bytes out of a sandwich sometime. Special materials and processes are a must, naturally. So that you can plot circuit patterns like this and whittle them down with special cameras to come out like this. Accurately producing the ultra-tiny is no easy job, and the organization of thousands of circuit packages is another tough one. You need a very sophisticated computer-aided system to do it. We have one called design automation. Design automation people must determine the most efficient arrangement possible for every component and conductor in the circuits that go into our products. This means working with the components and systems manufacturing divisions, providing them with all the logic and packaging and test information they need to make circuitry like this. These design automation engineers in Poughkeepsie use special programs in their time-shared engineering information system to record and update circuit design data and to simulate the way the circuit should work. They found these terminals are like open doors to the computer they use. If you make a mistake, for instance, you know about it right away. These terminals have cut average turnaround time for many jobs from days to hours. No matter where you go in our laboratories, finding new ways of doing things is a way of life. In San Jose, for example, a special kind of glass has to be created to make new tape and disc heads. It's pulled into thin rods under rigid size and temperature controls, and then used as binding agents for the materials that go into the new heads. Magnetic heads are, of course, very precisely made, and in the case of discs, there's practically no margin for error at all. Here's how they test their discs in San Jose. This machine can find impurities in the magnetic coating itself, as well as any tiny surface faults. The head on this disc tester, by the way, is made with those glass rods you saw a moment ago. To give you an idea of how fast the new heads can perform, here's a look at the heads on a disc drive developed a few years ago. Now you're going to see the new ones in action. Testing takes on many other interesting forms. Here's an unusual one. This is just outside the RFI test site in Birmingham. RFI stands for Radio Frequency Interference. Inside the building, made entirely of wood and plastic but without a single nail, engineers measure the static radiated by our machines. This remotely controlled antenna picks it up at various distances and heights outside the building. The reason for all this is that we want to reduce the amount of radiation interference any machine can cause, the kind, for instance, that sometimes messes up your TV picture. So engineers built this special metal-free chamber to carry out delicate radiation tests and simulate a wide variety of environmental conditions. Many IBM customers write their own programs and arrange their systems for their own needs. But when industry needs a special system, our industry and application systems people go to work. In Raleigh, they engineered the new brokerage system. Its executive console terminal, along with special programs, puts things like complete portfolios and the latest stock prices literally at the fingertips of stockbrokers in a matter of seconds. Each morning at the beginning of operations, the control programs are loaded from this special disk. It's quick and easy. Now we're in an applications lab in Raleigh. We really are. It was turned into a small supermarket to help design a supermarket store control system. It streamlines the checkout process by recording price and product information automatically while gathering other data for store management. Code numbers are keyed or read optically into the system. Here, they're carrying out a performance comparison of the two. Items are displayed with their prices, while the information is stored for later transmission to the main office of the supermarket chain. That way, the main office gets a complete picture of the day's activities within hours of closing time. Fast feedback like that will be very important in improving their profitability. Well, that wasn't a real supermarket, and this isn't a real hospital. This medical terminal in Kingston lets a nurse put information into a record just by sliding this little optical reader over the information. It's immediately displayed and can be recalled at any number of locations throughout the hospital instantly. She doesn't even have to worry about the doctor's handwriting. This is not another applications lab. They really do make cars here. This is the Volvo plant in Göteborg, Sweden, one of our customers. Staying on top of our customers' needs is part of the development process. And what better way to do it than to talk directly with them? Here, Dutch programmer Jan van Balkum is visiting Volvo to find out about their changing needs and to get a better idea of what we can do to meet them.
From the Dutch laboratory has put together a questionnaire that we will later on answer in more detail. But let me ask you something to begin with about your installation. I believe you are running under OS, is that correct?
We're running under OS our two main computers, 65 and 50.
65 and 50. And I've seen even more CPUs, have I?
We have a 40 running DOS in a dedicated system.
I see. Especially the dataset utilities are of great interest. You made a special remark about these.
When we aren't making the action, we go where the action is. Okay, you know what this is. And these. And these are familiar. Suppose you could create directly linked electronic networks for these communications instruments without any of this in the middle. Faster, cheaper, and a lot more versatile. It's called Carnation. An earlier version of this system was developed here at Lagode for European use. Supporting the French people on development of the system's control units are these engineers at the Nordic Lab in Lidingö, Sweden. This unit was designed around conventional magnetic core memory, while this one is being built to use those tiny FET memory chips you saw earlier. Hard to believe, but the entire memory will go right here. The power supply in this version represents a new technology too. Developed in Kingston, it's transistorized. It's more reliable, a lot smaller, and cheaper, and a lot lighter than this earlier one. Kingston is working on a complementary communication system called Rosebud, along with new terminals, like these data and credit card readers that exist nowhere else today. These are two of several SDD projects serving communication. Others being developed under U.S. government contract help speed the mail. Engineers at Rochester have come up with this system that reads addresses on letters and sorts them at 12 a second, or if you like big numbers, 43,000 an hour. Letters are zipped across a special optical reader by the vacuum-operated conveyor. With an intense beam of light, the reader scans the address, and the letter is fed into a controlled device that routes it through another conveyor into a box for its particular destination. This Endicott machine makes the letter carrier's job easier. It's called a carrier sequencer, and it takes all the letters in a given postal route and arranges them in the order the postman will deliver them. The postman's house-to-house route is fed into the machine's memory, and the letters are sorted at more than 30,000 an hour. No matter how well our products perform, we are always looking ahead. Here in Endicott, we're working on 2 new printers for a wide range of low-cost terminals. This one is among our smallest. Instead of using the familiar Selectric ball, it has a rotating character wheel. A tiny hammer strikes the proper letters as they pass the printing position, up to 30 times every second. And this one uses a metal band with all the characters embossed right into it. A series of little hammers strikes the paper against the band as the proper letters pass by. As small as it seems, it can print over 150 lines a minute. We'll be seeing it soon in many new products. For several years, IBM has produced publications in Braille. But Charlie Hart, a Boulder programming writer working on a creative development grant, has found a faster, much cheaper way to do it, by computer.
We've had books, Braille books produced by computer before. The American Printing House for the Blind is doing this now with IBM's help. They go to punch card, from there to a special embossing machine, from there to the printing press and Braille books. And what I'm trying to do is get rid of this special embossing machine and come out with a process to go straight to the printing press with some conventional process. And the way I'm doing it is with photographic etching. This is what we get. This is a Braille plate made by etching computer printout.
Quite an example of what you can do when you try. They've got quite a feel for new ideas at Raleigh, too. This one, the mobile terminal, has already become a new product. And yes, it is quite mobile.
Come in 154. 10-7 on car check, 1971 Plymouth, brown in color.
Okay, he's pulled someone over. He keys the plate number into the terminal. It connects him directly to a computer information center. So in seconds, he has a printout on the suspect car. Owner, registration, outstanding warrants. The Kansas City, Missouri police have tested the MT, and they were impressed. A few days after they got a test unit last March, it was used on a routine check, like this. And the driver was arrested on the spot because the MT reported the car was stolen just 20 minutes before. These terminals get interesting, don't they? They've got us in the transit business, too. San Jose has developed an automatic fare collection system for San Francisco's Bay Area Rapid Transit Authority. You buy a magnetically coded ticket for, say, $10. When entering and leaving the system, you put the ticket into a gate console. Use the same ticket for any combination of rides until you've used it all up. This experimental non-coded information system lets computers handle drawings, graphs, pictures, even handwriting. Working together, STD and ASTD have developed an important new direction for our products. In addition to getting the usual coded data from a keyboard or other machine, special readers, like this laser scanner, sense the images of documents, something like an electronic snapshot. Computers can store the images, combine or separate them, or create new ones. By manipulating NCI electronically, computers can create newspaper layouts, weather maps, or engineering drawings. Insurance companies can handle complex forms, signatures and all. And oil companies can scan credit card slips and produce bills like this, quickly and easily. In STD, development doesn't apply to machines alone. There couldn't be new systems or a leading edge of any kind without people. So we also help develop careers. Monroe Miller, along with others in Harrison, is part of our continuing commitment to improving career development opportunities for all employees.
I'm sure that many share the concern, or what I see as a big challenge, that being one of managing work in an ever-changing environment brought about by technological evolution and revolution. We only have to recall the dramatic change as we went from 7 to 10 to 360 to System 370, and now we're talking about something called future systems. This thing called future system promises to be an exciting era, but it's going to demand more from all of us. Managers are going to have to manage in an ever-changing environment. Employees are going to have to work or contribute in an ever-changing environment. I have some concerns and I worry about maintaining an environment where employees continue to see or perceive job satisfaction as a possibility, job challenge, job content, career growth opportunities. Employees are going to have to assume more responsibility for their careers, and that they will have to play a bigger role by staying technically current, technically involved, such that they might sustain their contribution to the IBM company. We're all going to have to be more inquisitive, more versatile, more aware, if we are to make future systems a success that the 360 was, that the 370 is. I'm sure I speak for everyone in STD when I say I accept the challenge.
While our people develop their skills for the future, advanced concepts and projects for the future begin to evolve into reality. An example is Kingston's new display unit that works with neon gas. Thin and compact, it's smaller and more reliable than the conventional cathode ray tube. There's a matrix of fine wires in these panels. Images are made by passing electrical current through selected wires, producing a small neon light where they intersect. The gas panel is being studied for uses where compactness is necessary. Using miniaturized circuits and a very flat keyboard, this terminal uses an ordinary telephone line to communicate with a remote computer. Slipped into an attaché case, it may someday put businessmen online with their computer systems from just about anywhere. This is something else. This Hersley terminal not only provides multicolored displays, but offers a few other new wrinkles. Sue Hall, in special engineering at Hersley, explains how it's used in a system her group is working on for controlling power distribution.
We have written a demonstration program which simulates a situation which could exist in a real power network. On the screen we have a picture of an imaginary power station. A situation has occurred now. We have overload on feeder 7. The operator has moved the cursor up to the circuit breaker. He types in a message to the computer to open that circuit breaker. He then sends that message to the computer. The computer confirms to the operator that the circuit breaker is to be opened. The operator then actions that action. The computer opens the circuit breaker, zero current being taken by that feeder, and a message left to investigate the feeder.
Terminals come in all shapes and sizes. So do keyboards. This is a Calico keyboard. In Raleigh, engineers can develop customized keyboards in just a fraction of the time it used to take by arranging these individual switches in patterns and mounting them on printed circuit cards. They're cheaper and more reliable than mechanical keyboards, and you've already seen them in action on the Mobile Terminal, Supermarket System, and System 370. These Calico keyboards are part of a whole new direction in system design.
One of the new developments in the company for building terminal communication subsystems is to start off with a series of building blocks, I/O devices, storage devices, communication adapters, and controllers, the heart of the terminal device.
This is Bill Chapman, describing a new way to design and build terminal subsystems.
For example, for the retail store system with the UC0, this block right here, we can add a certain quantity of memory, a keyboard, and a gas panel with associated adapters, and a binary synchronous adapter to communicate back to a host processor. If we want to design a terminal for the insurance market,
these universal controllers, combined with some of the printers, keyboards, and memories we've been looking at, represent a fast, new approach to system design. Another innovation for the future. In SDD, the words future and challenge are almost synonymous, and that's especially so for IBM fellow George Judson at Endicott. He's developed 2 machines for the medical treatment of blood. This is one of his development team members using the blood cell processor. This machine processes 1 red blood cell unit at a time, making it economically possible to store rare blood types and produce a purer blood unit. That can reduce a patient's reaction to such diseases as hepatitis. Dramatic? To medical men it is, and so is the blood cell separator. It takes whole human blood, separates it into its major parts, and removes certain ones, such as plasma or red or white blood cells. The process has been used to clinically support leukemia patients and others with abnormal plasma conditions. Everything SDD does as a key component of the IBM company is a commitment to assuring our leadership in the computer industry. This is the Announcement and Special Review Committee in Harrison, representing every division that plays a part in bringing a product to our customers. Its job is meeting that commitment by assuring that product releases and announcements will support IBM's leading edge. SDD's Tom Kober, A&SR Committee Chairman.
A&SR Committee performs a staff function for the DP Product Group General Manager. And the purpose of this committee is to review all of the releases for announcement to assure that the commitments have the full support of each of the individual divisions that are required to implement the action that's described in the release. And also to assure that the releases are consistent with the policies and practices and the overall objectives of the IBM company.
Commitment. This is part of it. In Boulder, IBM's Center for Tape Technology, this massive future storage device is part of it. And so is this, an advanced optical reader at Outhorn, still in early development. Documents fed into the machine will be read automatically, line after line, document after document. Its scan head was developed in Rochester around two components, the LED array and the photodiode. The LED, or light-emitting diode, shines a concentrated beam of light onto the document, and the photodiode senses or reads it, like this. And then there's this non-impact printer at San Jose. This is one of several test models that can print over 10,000 lines every minute. Maybe some advanced model will use laser beams for printing. The future, of course, will tell.
All this is fine and confirms the general concepts we have established for our mission. What we should discuss now are the Vienna contributions to FS. I would hope that you bring certain results from your discussions in Poughkeepsie earlier this week.
To a lot of SDD people, the future is their job, and it's not something that will just happen by itself. In Vienna, the fabled Tower of Babel is a constant reminder of that, for the future is as real as tomorrow's failure or success, because that is where either will lie. This group in Vienna develops future programming ideas, languages, applications for SDD's products of tomorrow.
In particular, we can investigate possibilities of extending the system. So we shall look for possibilities of adding boxes of memory and adding processor boxes without disrupting the working of the system.
Was there any preference as far as symmetric or asymmetric interconnection is concerned?
The present thinking is...
These ideas, these concepts, can one day be vital to our future systems. This is Dick Case, Director of Advanced Systems.
Well, this product, FS, is intended to be IBM's next major full system development project to cause a revolution, if you can use that word, in the data processing industry that's bigger than things that we've seen for a decade. The company and the industry faces a lot of serious problems, and we've really got to turn the industry around and make computer systems much more easily usable and available to the man in the street. Second major thing that's significant about this development effort compared to some previous development efforts is that we're kind of starting out under forced draft in a way, doing a lot of things at once. Thinking about users, thinking about technology, thinking about system development and architecture and design, thinking about programming support, all at the same time, when logically you'd like to think that those things were sequential, and first you discovered what the user needed, and after you had well understood that, then you discovered how to architect the system, and after you'd well understood that, you figured out how to implement it. Our view is that that serial process is going to take too long. The company, the industry needs the FS system before the results of that, so we're putting things in parallel, and we're looking at users, and we're looking at architecture, and we're looking at technology, and we're looking at system design and development all at once. We have a worldwide development effort from the outset. Of course, we had a worldwide development effort on 360, but the number of locations involved...
We're changing the way we produce our manuals, and we can no longer produce Braille copies the way we used to. And change is what I find to be the most exciting part of the job. And the job is so interesting that I find it very difficult to work on this project. I haven't got much done yet. It's not a problem of management, it's a problem with me. Everything about the job is so challenging. Everything clamors for attention all the time. And, you know, I can't understand how anyone in SDD could ever be bored. There are so many things that require doing.